Hello, my dearies, and welcome back to the channel. Science Stuck, or maybe just welcome to the channel because here we have opened a new channel for you guys, which is going to be a sole channel dedicated to physics, chemistry, and biology for the class 9th and 10th students of the Icse board. Without any further ado, I would like to get into the chapter, which is the first chapter of physics, which is force. So, if I want to talk about force, as a junior student, when you would have heard of force, you would have always said it is a push or a pull. Push or a pull. Next, what would say is it may change the state of rest or motion of an object. As the first law given by Newton implements. What does it say? It says that a body at rest would continue to remain at rest and a body at motion would continue to remain at motion until and unless an external force is applied on it. Thereafter, we'd see it might change the direction of motion. The best example I could give you for this would be hitting a ball with a bat. So, there's a ball that's approaching this way, and the batsman hits it, and the direction of motion of the ball changes. Next, another thing would be changes the shape and size of an object. Okay, now let's see what has been given to us. अगर एक rigid body हो, okay, when force is applied on a rigid body, cause only motion in it, whereas when it comes to a non-rigid body, when we apply force to it, the size changes, the shape changes, or even the state of motion or that of rest could change. Got it? Sorry. Now, in mathematical form, on a in mathematical form, force. Now, talking about force in mathematical form, force is supposed to be dp by dt. Now, one would ask, what is d here? It is nothing but delta p by delta t. Now, if there is a small change in p or small change in t or any other physical quantity, so we write that change as small d. Okay, now dt. Now dp by dt. Okay. Now what is p here? P is momentum. This brings us to second law of Newton, which is force is directly proportional to the rate of change of momentum. Okay. Now this is momentum, and momentum, the change in momentum per unit time is written as force. Now, momentum is nothing but mass into velocity. This becomes dmv by dt. If mass happens to be constant, dv by dt, because m is constant, so we bring this out of the bracket, right? Now, dv by dt, delta v by delta t is nothing but acceleration, right? I'd ask you to take notes simultaneously while I'm teaching you, because this is, I guess, one of the rare videos where you are going to do line by line Selina. which is, I guess, the only book or the book that majority of the schools use for the ICSE board, right? So take notes alongside, or you might also mark in your book itself. So this becomes MA. Okay, that's the formula for force, right? The force is a vector quantity. What is a vector quantity? That has direction, as we've learned in the junior classes already. Now, if as a science person I would have to give a detailed explanation of a vector, I would say obeys the vector law of addition. But as of now, what you would say is simply referring it to as direction. Okay. However, this statement which I've just mentioned here will also help us a lot in the following part of the chapter. Okay, the SI unit, standard international unit, is going to be your Newton or kilogram force. Now comparison between 1 Newton and kgf is supposed to be done. Now for this, let us consider we have a 1 kg mass. The force experienced by this object because of gravity is going to be ma, and acceleration is acceleration due to gravity, so we write it as mg. Mass is 1 kg and g is 9.8, so 9.8 Newton. So kgf, 1 kgf is the gravitational force experienced by 1 kg object. Now if you had to convert 1 kgf to Newton, you would use this derivation. Okay, I've explained how you landed to this, right? Now in the, now we haven't started the chapter so far, as in not the exact chapter. So I'd request you that as I go around with the chapter, what you do is I'll be marking the keywords. You mark the keywords. Thereafter, you also try making short notes, because it is difficult to refer to a lot of material while you are going to study for your last moment. But if you have everything written at one place, it will become easier. As it is, this book is a lot self-explanatory. So once you have heard the lecture, or once you have gone through the lecture, and the next time when you sit down with only your book before you, without the screen, you would have everything jotted down on your book. So when you look into your book, you would get flashbacks, and thus it will become easier for you. Right, students? Now let's get into translational and rotational motions. Okay, now as we have read above, rigid body, okay, rigid body would show motion. Okay, it would not show change in shape or size. So motion, if you are talking about here, this we are going to see for which of the two cases. This one is, this takes rigid body. Okay, so here one condition that needs to be fulfilled is rigid body. Let's get into linear or translational motion. Okay, so linear motion or translational motion, it means in a straight path. Straight path. Okay, students, mark this. Straight path requires a stationary object, rigid body. Also, it must be free to move. What is the condition? Free to move. Example would be pushing a ball lying on the floor. That next, sorry, rotational motion. If the body is pivoted, that is, it is not free to move. Condition required is pivoted. That's to a rigid body that is pivoted at a point and a force needs to be applied. Thereafter, the body would rotate about its axis. What happens is body rotates about its axis. So characteristic for linear translation motion would be it moves in a straight path. Here it rotates the body about the axis passing through the pivotal point, right? Now let's get into the example straight away. Okay, sorry. For example, if a wheel is pivoted at the center, now let's just talk about a car wheel. Okay, there's axle and there's another wheel, right? The friction force causes it to move. There's a force applied this way in case of this wheel, right? Here we applied a force, and now because of this force, this wheel would move about its center. Okay, force is applied tangentially, that is through a tangent, and this rotates the wheel about what? About this given pivoted point, right? The same is the case when you are going to talk about a door. Let's get into the door, right? This, say, what's wrong with my drawing? Yeah, let's just draw a shape using, yeah. Yeah, let's say this is the door. Let's add a knob to it. Okay, that's the door knob. Now you apply force, say push the door opens this way, right? Door opens up this way. So this is what? This is nothing but rotation about the hinge, which is here. Okay. Now, moment of a force or torque. Moment of force. It is nothing but the turning effect of force that takes place when this force is applied at a suitable point on a pivoted object. Now, let's do a fun activity here, students. Let's just take a notebook and place it on your finger, as in balance it on your finger. Okay, now your finger is going to serve as a perpendicular axis to your notebook. And now if you apply a force this way, your notebook is going to rotate about your finger. The same is the case shown in figure 1.3. Here what we do is there is a force that is going to be applied here this way, right? The line of action of force is where, in which direction the force is being applied. So if in this case this is my F, okay, this is, let's say, my OF. In case of my notebook, this OF is supposed to be my line of action of force, whereas in case of my diagram 1.3, okay, you see that this is your line of action of force, which is going to be your FP. What is your line of action of force? FP. Okay, now you have the axis of rotation. Axis of rotation, what is supposed to be axis of rotation? Perpendicular line passing through the point O. What is your axis of rotation? Important question. What is your axis of rotation for this diagram? Okay, it is supposed to be perpendicular to the pivot. Okay? So take a note of this. Where I perpendicular distance. Oh, sorry, this is not going to help. Okay, so I'm just writing it down here. Okay, what is your axis of rotation? Axis passing vertically through the point O. Okay, axis of rotation. Important questions because this might not come in your board exams. However, this might end up becoming your base for this chapter. So I'd request you to kindly focus here. Okay, next we applied a force here, therefore the body started to rotate this way. However, we see that factors that affect the turning of the body are going to be what? Magnitude of the force applied. With how much force you apply, you I mean, what is the amount of force you apply? What is the magnitude of force that you're going to apply? So when you're rotating a notebook, you see, once you just touch it a little bit, okay, in this direction, you'll see little bit movement. Thereafter, if you apply more force, what will happen? This is going to rotate better. Yeah. Now, next is the distance of line of action of the force from the axis of rotation. So distance of line of action of force. This is your line of action of force. Line of action of force. Right? FP is supposed to be a line of action of force. Now axis of rotation is perpendicular to the point O. Perpendicular to the plane passing through the point O. Right? This one. This one. Now a perpendicular distance between these two, which is going to be a OP. OP is going to be a perpendicular distance between the line of action of force and the axis of rotation. This is supposed to be the distance which is going to matter. Right? Indeed, the turning effect on the body depends on the product of both the above stated factors. So the product of the two matters. So what is happening here is if one decreases, the other has to increase in order to balance out each other. Right? Now, this product is called moment of force. Done. What is the product supposed to be? This product is supposed to be the moment of force. You write moment of force as force into perpendicular distance between the line of action of force and the axis of rotation. Perpendicular distance of force from the point O, which is what is point O? This is the axis of rotation, right? Now, thus the body rotates due to the movement of due to the moment of force. So it is not the force that causes rotation, but the moment of force which is going to cause rotation. You can say force causes rotation, but it is indirect, and not every force can cause rotation. However, every moment of force can cause rotation, right? Now, the turning effect of on the body about an axis is due to the moment of force applied on the body. So turning effect, why does the turning effect come into action? Because of the moment of force applied. Movement, measurement of moment of force. How do you measure it? As we have already read above, it is the product of the magnitude of the force and the perpendicular distance of the line of action of force from the axis of rotation. Done. Let's see. So moment of force into perpendicular distance from of the line of action of force from the axis of rotation, which is going to be F into OP in the case of figure 1.3. Now let's see this. Okay, this is a very important note. Mark it. Let's see what does it say. for producing maximum turning effect on a body for a given force. The force is applied on the body part at the point for which the perpendicular distance of line of action of force from the axis of rotation is maximum, so that the given force may provide the maximum torque to turn the body. So now, say this is your door. Very simple activity. Okay, apply a small force here and approximately the same amount of force here. Okay, you'll see it is easier to rotate it when you apply the force at point X as compared to that on point Y. Or even on normal circumstances, you do not open the door, pushing the door through point Y, because it becomes really difficult for you. Like, I mean, you could try it out on yourself, or you could just notice sitting here itself in front of the book there. You always apply force where the knob is situated, not away from the knob towards the hinge, right? Now, unit of moment of force. So this, I hope this activity has explained you this note and the importance of what this note is going to play in your day-to-day lifestyle, and also in the upcoming sections of this chapter. Right? Now, units of moment of force. What are the units? It is nothing but Newton meter when it comes to your SI unit, which is supposed to be denoted as Nm. Right? The CGS is going to be 9 centimeter. 1 Newton is supposed to be 10 to the power 5 dyne. Right? And 1 meter is supposed to be 100 centimeter. Therefore, 1 Newton meter is 10 to the power 5 dyne into 10 to the power 2 centimeters, which becomes 10 to the power 7 dyne centimeters. So if I want to ask you what is 1 dyne cm, your answer is supposed to be 10 to the power minus 7 Newton meter. Reciprocal for this one. Right, students? Now, we've already discussed 1 kgf equals 1 Newton and 1 meter equals 1 meter itself. No point discussing that. So 1 kgf meter becomes 9.8 Newton meter. Now 1 gf into centimeter equals 980 dyne centimeter. Clockwise and anti-clockwise movement. Clockwise. If a body is rotating in the clockwise direction, this is supposed to be the clockwise direction. This is considered as negative. Whereas when you talk about the clockwise direction, if you rotate it this way, anti-clockwise, this is supposed to be positive. Let's just read through it. Conventionally, this is a convention given. Okay, if the effect on the body is to turn it anti-clockwise, the moment of force is called the anti-clockwise moment, whereas it is taken as positive. While if the effect on the body is to turn it clockwise, the moment of force is supposed to be known as, students, clockwise moment, and it is taken to be negative. Done. Now, in the next chapter, which is going to be your work power energy, okay, you will see that Newton meter is going to be written as what? Joule. Okay. However, in this chapter, you cannot write so, because your torque is nothing but a vector quantity. So, a vector, when Newton meter is supposed to be written as Newton meter itself, but when it comes to work, when it comes to energy, Newton meter is going to be written as joule. Why? Because work and energy are both scalars, right? Applying the pivot force on the pivot, its direction of rotation depends on the point of application. Now, if you apply on this point, it is causing a clockwise movement, whereas if you're applying it this way, anti-clockwise movement is going to be seen. Okay. Next is direction. If I apply at this point itself, direction is this, clockwise. If I apply it this way, anti-clockwise. Done, yeah? Let's get into examples. Quickly we'll go through to the examples, and then we can get into your couple and equilibrium and all of that, so that in the next video we can discuss another part, which is going to be your center of gravity, right? Center of mass. Now, common example of moment of force: opening and closing of a door. We've already discussed this above in the activity which I discussed with you guys, right? So this is your door. To open a shutter door, we apply a force F normal to the door at the handle P. Oh, I guess they've given us a diagram. Yeah, this is the handle P here. So they apply force there, right? So which is provided at a maximum distance from hinge. So that Y is hinge. So now Y is the knob. Write it here, okay, students. I can't write it here because my stylus does not permit me. You can write it here as a short question, because this might appear as a give reasoning question. Why is the knob situated as far from the hinge, right? So that answer is supposed to be, so that the sorry students, so that the perpendicular distance between the line of action of force and the axis is maximum, so that maximum torque can be obtained. Done. That is it you need to know from this section. Okay, about the door example, this is the thing that you need to know. Because why am I saying it, that making the distance will bring out the maximum torque for a given force? Because your what is your moment of force? Moment of force is nothing but force into perpendicular distance. Now if the perpendicular distance increases, so for any force, the perpendicular distance if increased would bring about more moment of force as compared to the smaller perpendicular distance, right? Next, upper circular stone of a hand floor grinder is provided near the rim. You might have seen, or you might not have seen actually, because it is not used anymore in the urban areas, right? So it is something like that. And then you have, you know, a handle here. This is supposed to be a handle. So you rotate this, and whatever is provided here, say your wheat, okay, is going to get grinded. So this is supposed to be farthest from the rim. It is not going to be provided near the rim. Okay, so that maximum torque can be obtained. What is the objective? Max torque. Right? For turning a steering wheel, force is applied tangentially on the rim. You'd see this way, or you'd see people apply force this way. There are videos on YouTube where you see people driving and they move their hands so smoothly through the steering wheel, right? So that's going to happen when force F is applied at a point A of the wheel rotates anti-clockwise, the wheel rotates clockwise when force F is in the same direction, is applied at point B. So now what how does the direction of rotation change direction of rotation. Point of application of what? Of force, and direction of application of force. That. Now, in a bicycle, to turn the wheel anti-clockwise, okay, small force is applied on the foot pedal of toothed wheel. Toothed wheel is what? Of size bigger than the rear wheel. This is your toothed wheel. Now, as you can already see in the diagram, this is a bigger wheel. So, in order to move the vehicle, you apply force here. So that a small force also when applied is going to bring about a large moment of force, and therefore this is going to have a chain across it which is going to join both the wheels together, and these wheels would move because a force is applied on the toothed wheel, which is going to bring about moment of rotation in the toothed wheel, and because the two are connected, the axle of the rear wheel would also show rotation about itself, right? Now the spanner, you must have seen, no, this one. You apply force this way, you don't apply force this way. This one, the because the nut is quite tight, a lot of force is required. I mean, movement of force is required. So what you do is a small force also if you apply here, okay, a bigger moment of force is going to take place because the perpendicular distance is going to increase. Because what is the perpendicular distance? Perpendicular to the nut bolt. So this is going to rotate this way. Done. Now, conclusion from the above examples, we conclude the turning of a body about an axis depends not only on the magnitude of force but also depends on the perpendicular distance of the line of action of the applied force from the axis of rotation. Larger the perpendicular distance, less is the force needed to turn the body. So perpendicular distance अगर ज़्यादा हो जाता है बच्चों तो क्या हो जाएगा, तो स्मॉल फोर्स में भी हमारा काम बन जाएगा. फिजिक्स आने से ज़रूरी नहीं है कि आपको बहुत ज़्यादा फोर्स चाहिए हो. You can use levers, you know in the upcoming chapters we learn about levers, about machines. Okay, so the load arm, the effort arm, the fulcrum, the load, the effort. Okay, now opening a bottle could be difficult, but a bottle opener could be used, which would make task easier for us, right? Now let's get into couple. What is a couple? A single force applied on the pivot point alone does not cause rotation of the body. Actually, the rotation is always produced by a pair of forces. In the above examples, now in the above examples, as I say above examples, the students might ask, "Ma'am, why are you saying that in the above examples? But we applied force only once at one point. We applied only in one point. We do not apply in another point." This, my students, you see, the rotation is due to force externally applied and the force reaction produced at the pivoted point. Which law? Third law. What is the third law? Every action has an equal and opposite reaction. So the reaction force and the action force together provide us the couple forces. Okay, the force of reaction at the pivot is equal in magnitude but opposite in direction. Action, reaction pairs are equal in magnitude but opposite in direction. Then, now the moment of force of reaction about the pivot is zero because its distance from the axis of rotation is zero. So the force of reaction at fixed point is not shown in figure 1.3 to figure 1.8. Okay, so what are we saying is the moment of force of reaction about the point pivot is 0 because its distance from the axis of rotation is 0. If the distance, perpendicular distance, is 0, moment of force would be 0 because perpendicular distance is one of the parts, one of the terms of the product, right? Such a pair of force is called a couple. Thus, two equal and opposite parallel forces not acting along the same straight line. What are we saying? See, what is happening is, say, in case of the spanner, let's say, okay, let me just rub this for you guys so that you can understand better. Now, I am applying a force in this direction. Okay, this is coming in this direction. So what are we saying? In the same straight line. This is not happening in the same straight line. This is one direction, this is another direction, right? So opposite forces not on the same straight line. This is going to cause the coupled forces. Then a couple is always needed to produce rotation. For example, when you open a door, rotation is produced by a couple of forces, right? Consisting of two forces, the force which we exert at the handle of the door and equal opposite force of reaction at the hinge. In case we require a large turning effects, two forces equal in magnitude and opposite in directions are applied on body explicitly. Students, you are going to apply explicitly for larger turning effect. Done. Right? Now, example for this one is going to be car wrench. A lot of force is required. A wrench, again, a lot of force is required. So what you do is you apply force this direction also and this direction also. Here, this direction and this direction. Two forces. Okay. This forms the wrench arm and therefore what happened? This is the wrench arm and therefore a rotation is going to be caused. Done. We've come quite far, if you see. Similarly, turning a water tap. This is going to be a water tap. Okay. Applied force this direction also and this direction also. Bottle opening, same case. Here, here. Okay. You're applying this way also and this way also. Turning a key. Steering wheel. One you push it this way, another side you pull it this way. Next time you open a tap, right? Turning a tap on. Okay. When you open a cap of a bottle, think of it. In fact, I'll tell you what, while you're flipping the pages of your book also, okay, a greater force is required when you're flipping it from the part where the binding has been done. Whereas when you're away from the binding part, where you're at the edge, and then you flip it, that's easier. So even flipping your book involves what? It involves what? Your couple or your moment of force. Moment of couple. What is moment of couple? Moment of couple is the moment of force that is produced because of a couple forces. Now, total moment of couple, that is going to be because of force on F at point A. Look, this is your body where in one direction this way and another direction this way force is going to be applied at point A and point B respectively. Now point A also we're going to see anti-clockwise, it's going to cause rotation, and B also it's going to cause anti-clockwise rotation. Okay. Now moment of force at because of force at point A is going to be F into OA because this is going to be a perpendicular distance between the line of action of force and the axis of rotation. This is going to be AO or OA, right? Moment of force F at end P. This is your force. This is your perpendicular distance between the line of between the axis of rotation and the line of action of force. FOB. This is going to be anti-clockwise. Now FOA plus FOB. Take F common, OA plus OB. What is OA plus OB? OA and OB. This is nothing but AB. Now AB is written as couple arm. Okay. Either force, that is going to be either point पे जो force लग रहा है, that is F, and the perpendicular distance between the two forces. Oh, we've already gotten into equilibrium. Now, equilibrium of bodies. Now, if you're going to talk about equilibrium, what is equilibrium? That is, it is going to have stability, right? Equilibrium is stability. When a force acts on a body, it can produce translational motion, right? If the body is free to move or can produce rotation. Now, if the body is free to move, translation. If the body is fixed, rotation. But it is possible to apply a number of forces such that result of all the forces is zero, so they do not change the state of rest or of motion of the body. The algebraic sum of moments of all force about the fixed point is zero, so they do not change the rotational state of the body. Then the body is said to be in equilibrium. When a number of forces acting on a body produce no change in it, state of rest or of motion or of rotational motion, linear and rotational motion both, the body is said to be in equilibrium, right? So now what we're saying is force net is supposed to be zero, right? Kinds of equilibrium: static and dynamic. Static means it is going to be in the state of rest under the influence of several forces. Now there's a book kept here on the table, right? Gravitational force, normal reaction force. I am pulling it this way, you're pulling it this way. Net force, say I'm pulling it with FA and you're also pulling it with FA, right? So FA is going to cancel each other and the normal reaction is going to be equal to the gravitational force applied. Therefore, what we are going to see, there's going to be a static equilibrium. Next is a book lying on the table. Oh, we've already discussed that. We've discussed both this and example 1 and 2 in the diagram which I've drawn here. In a beam balance, when a beam is balanced in a horizontal position, this is supposed to be a beam balance, yeah? I don't know what it's called in Hindi, but I guess it's tarazu. Something like that. Yeah. So if I place 1 kg here and I place 1 kg here and I hold it from this point directly from the middle, right? What we're going to see is that it is going to show static equilibrium because the force experienced in this direction and in this direction, it is in anti-clockwise. So this is going to be clockwise, yeah. This is going to cause clockwise movement and this is going to cause anti-clockwise movement about the point O. So sorry students about the anti-clockwise thing, right? This is going to cause clockwise. This is going to cause anti-clockwise. What you're going to see is anti-clockwise moment of force due to the weights on the left pan, and that on the right pan will cause clockwise moment is going to be equal, and therefore you're going to see that an equilibrium is going to be established, which is going to be what kind of equilibrium, my students? This is going to be your static equilibrium. Let's go into dynamic equilibrium, that is going to be about the state of motion, which is going to be either translational motion or even rotational motion. Raindrop reaches the earth's surface with constant velocity. Constant velocity means acceleration is going to be zero. That means F net is going to be zero. The weight of the falling drop is balanced by the sum of bound forces and the force due to friction of air. Thus, the net force of the drop is zero. So it moves with a constant velocity. And acceleration. Sorry. An aeroplane moves at a constant height when upward lift on its balance lift on it balances its weight downwards. So what are we doing? It's going to move upwards, that is, it's going to apply force upwards, whereas it is going to balance its weight downwards. So F net again becomes 0. Therefore, moves at constant height. That is going to be constant velocity. That means acceleration is again 0. Stone tied at the end of a string and you whirl it. Whirled in a circular path with uniform speed is dynamic equilibrium because the tension is along the string. And centripetal force. What is centripetal force? A force that is going to be experienced towards the center of the circle, and tension is going to be outwards, right? This is going to be balanced. Similarly, the motion of a planet around the sun. Now, centripetal force in the case of your whirling of your stone is going to be balanced by tension, whereas in case of planets it's going to be balanced by gravitational force, whereas when it comes to atoms, the movement of electrons about the nucleus is going to be balanced by which force? It's going to be by Coulomb's force, right? Which is going to be an electrostatic force. Condition for equilibrium. When you're going to talk about condition for equilibrium, it means that the force acting on it should be 0, and the algebraic sum of moments of all the forces, that is, the turning effect should also become 0. About the point of rotation should be 0. That is, sum of anti-clockwise moments about the axis must be equal to the sum of clockwise moments. That means इस साइड जो टर्निंग इफेक्ट आएगा वो इस साइड भी टर्निंग इफेक्ट उतना ही होना चाहिए ताकि ये इसको बैलेंस कर दे, है ना? सो व्हेन यू वांट टू टॉक, सो एज वी ऑलरेडी सेड, राइट, मोमेंट, sorry, anti-clockwise moment, you're going to take it as positive, whereas clockwise moment you're going to take it as negative. So when you want to talk of addition of anti-clockwise moment with clockwise moment, is going to be negative. The resultant is going to be 0 when both are going to have magnitude equal. Newton's principle of moments. When several forces act on a pivoted point, they tend to rotate it about the axis passing through the pivot. The resultant moment of all the forces about the pivot point is obtained by. Now, how are you going to obtain the resultant moment? Taking the algebraic sum of moments of each force about that point. Find the algebraic sum of anticlockwise moment is taken to be positive, while and clockwise moment is taken as negative, as discussed here already below, right? According to the principle of moments, if the algebraic sum of moments of all forces acting on the body about the axis of rotation is 0, the body is supposed to be in equilibrium. So no rotation is going to be seen. Okay. Physical balance or beam balance works on the principle of moments. We've already discussed it here. Right? Suspend a meter rule. What are you doing is we're going to bring a ruler. We suspend it horizontal. We're going to suspend it horizontally. Okay. At O shown. Now suspend two strings. Balances A and B on the meter rule with some slotted weights, weight 1 and weight 2 on either of them, either side of the thread. Now the meter rule might tilt one side, adjust either the sorted weights on the spring balance or position the spring balance on either side of the thread as shown. Now what you're going to do is either you balance it in such a way that both the weights become equal this way. Here you place it this weight and this weight equal. Now you balance it. Or what you do is you balance the moment of forces such that the product of W1 and L1 and W2 and L2 are going to be equal, right? So what you're going to see is the rule becomes horizontal when it becomes balanced. Now using this, what you can do is you can determine the unknown weights for some quantities. Now this is why the beam balance is going to be used, right? Because the beam is going to have the same weights on both the sides and it's going to have same length on both the sides of the suspended string. So the weight when placed to a standardized weight or a known physical quantity is going to balance itself. Now, students, look, I wanted to do the examples today with you, but it would be wrong. I feel what we must do is you sit down and you revise this entire thing, because it's not a small portion that we've done today. It's also quite a lot of portion, right? It has already taken us 50 minutes, 50 minutes so far, and now I'd say let's end it here. Study well. In the next chapter, I'd come up with these examples. I'll discuss a few important ones from here. Thereafter, we'd head into these. Let's discuss all of these in the next lecture. Okay, so I'm planning is we'll have these 18 numericals and a few examples that have been mentioned. If you have any particular doubt regarding any example, please comment down, and then in the third part of the lecture we'll come up with center of gravity. Okay, and then the no what we do is we do center of gravity, we do uniform circular motion all together, and then we hardly have any we don't have any numericals here. So yeah, we do we'll end this chapter in 3 lectures in that case. So in the next chapter we do examples. Okay, please students, please don't rely on me for doing the numericals on my own. You please sit down with a pen and a paper. You do it on your own, and the ones which you are unable to do, I request you first do it on your own, and then you come to me, you check the videos for your doubts. Now if you are unable to do anything, or if you see that I have done it in some other method, you could learn that, and this is going to help you only. This is not going to be any profit for me as it is going to be of you for you, right? So now all the best theories, keep learning.